So this talk is about probabilistic hashing. So I'm in the stat department, and the stat department is under CS or CIS. So this is a perfect fit. And nowadays people talk about big data. So if you view the data sets as a matrix, like of size n and d, so in modern applications, the number of examples, 1 million is very common, 1 billion is not rare. And if you think about click-through data, you really have an unlimited number of examples. And high-dimensional data are also very natural and common in imaging, text, and biological data. For example, it's common to use million or billion, and some papers use a trillion or 2 to the 64 or even higher as a convenient upper limit. So in a sense, the dimension can be arbitrarily high by considering pairwise, three-way, or high-order interactions. So now let's first motivate the talk using the classification problem. So this is binary classification. So we consider data sets. X has n examples in capital D dimensions, and Y is -1, 1. So the task is to predict Y. And we can train SVM, the linear SVM. So we just solve this optimization problem. We learn the weight, W. So the weight has the same length as the data dimensions. Or we can use logistic regression. And they perform almost the same, except SVM usually, or logistic regression takes usually 10 times more time than SVM, but the performance in terms of accuracy are almost the same. So let's list some of the challenges of high-dimensional, for learning from high-dimensional massive data. So first of all, the data itself may not fit in memory, and the data loading time may take us too long. For example, if you just say, I do an online algorithm, which requires much less memory, but then loading the data itself takes a long time. And if you have to, for example, iterate over the data several passes, then the data loading time is definitely the dominating factor. And the training time can be very expensive, even for linear methods. And the testing time could be expensive as well, and because especially for applications in search or some other user-facing application like interactive visual analytics. And another interesting issue is that the model itself may be too large to be stored. For example, this weight is if the data is 2 to 64 dimensions, you cannot really store the weights of vector 2 to 64 length. So there are numerous problems. And there's a popular solution, which is called random projection. So the talk is actually about minwise hashing, but I like to start with the random projection because that's something that everyone's familiar with. So basically, you have a massive data matrix A, then multiply with the skinny matrix. It's not just one column, it has k columns. And R, matrix R, to get another skinny matrix B. So B has only k columns and n rows. And if you sample the elements of R from IID normals, then B approximately preserve the Euclidean distance as well as the inner product between any two rows of A. In particular, B times B transpose is the same as A times A transpose in the expectations. So therefore, you would say, well, if I want to learn a classifier like SVM or logistic regression, what I need to do is, well, instead of using A, I just use B. Then the task is much easier. So that's simple. And so enough talking, so let's go to the experiments. And the interesting thing is that after I become a system professor for a few years, the longer I work in research, the more and more I like to do experiments. And so in the end, I feel like something that works is really the only thing that matters. So this is the experiment. So I have 3 data sets. So web span data sets is about 16 million dimensions, and I use a pairwise, the original MNIST plus a pairwise features to get about 200,000 dimensions, and there's another small data set. I included because it's dense. So most of the data set actually is sparse, but this data set is actually dense. So however, instead of sampling from a normal projections, we use what we call very sparse random projections. So the random matrix R is not normal. So instead, we sample from this distribution. So there's a parameter S. So when S is 100, so that means 99% of the entries are 0. So it's very sparse. And in fact, we can show that when S is 10,000, it still works very well. So that means the matrix is 99.99% sparse. It still works very well. So this is a paper in 2006. And so let's show the experiments. So what do we see? So this is a SVM test accuracies on the web span data sets. So the C is a parameter in logistic regression. Remember the C parameter. So logistic regression SVM has one parameter, which is C. And so for varying the C values, we get different accuracies. So then we, by increasing the number of projections from 32 to 4,000, we get a better accuracy. But even with the 4,000, we can see that we need more than 4,000 to achieve the same accuracy as using the original data. So that means random projection is good, but it's very expensive. You need actually more than 4,000. In our experience, usually if you do like 10,000 or 100,000, you get very good results with random projections. Yeah, if you can afford that, then that's good. And another interesting thing is that the sparsity parameter does not matter much. For example, you have 1 versus 1,000. So 1,000 means 99.9 of the entries are 0. You still get almost the same results as using the dense projections. So unless the number of projections is too low. But you need a larger K anyway. So the sparse projection works. And so this shows that even for 10,000, sparse, like 99.99% of the matrix entries are 0, it still works very well for large Ks. So as long as K is large, which is necessary for high accuracy, then the projection matrix can be extremely sparse. And so this is another data set. We can see the same thing. So basically, K has to be large. 4,000 is not enough for achieving the same accuracy as using the original data. But as long as you're using large K, then the matrix can be very sparse. So this is for SVM. And so I plot all of them from 1 to 1,000, or 100,000, 10,000 sparse. So as S increases more and more sparser, you still get the same results for SVM. And the same thing for logistic regression. So logistic regression and SVM, in terms of accuracy, they're almost the same. And so there's a small data set. We can see that with a 10,000 S, which means very, very sparse matrix, you actually get even slightly better results. So, but it's a small data set. So I'm doing a lot of repetitions. I only finished about 500 repetitions. Maybe I guess once I finish at like 1,000 repetitions, I'm going to see more consistent results. But the interesting thing is that as long as K is large, the projection matrix can be extremely sparse. And so that's classification. Now let's look at K-means clustering. So we do K-means clustering on this MLIS data set, and we evaluate according to the classification accuracy because we know the class labels. Normally you don't know, but suppose we know the class label, you can actually evaluate using the classification accuracies. So we can see that, so this is a baseline using the original data, and by varying the number of projections, you get a better accuracies, and as long as K large enough, the sparsity does not seem to matter of the projected data. So that's the summary of the advantages of very sparse random projections. And once R is very sparse, the matrix multiplication is much faster and much easier to store the R if necessary. Sometimes you don't store, you regenerate, but if much sparser matrix is much easier to generate. And it's also actually sparse original data, you get a sparse projected data. So it's actually sparsity preserving. So the number of zeros will be K times this formula. So this is very nice. So F is the number of non-zeros in the original data. So sparse data get a sparse projected data. So that's the nice thing about random projections. So what's not nice about random projection? There's only one disadvantage, only one. The only disadvantage is that it's not accurate for binary data. And we can see why it's not accurate. So let's do some analysis to see why random projection is not accurate. So let's look at the first two rows in A. We call U1 and U2. They're in D dimensions. And the first two rows in B, and it's V1 and V2 in K dimensions. K is much smaller than D. And so we can use the inner product of B to estimate the inner product in A. So that's the estimator. So we always use A to denote the original inner product. So A hat is the estimate. So the original inner product can be estimated without bias from the projected data of the inner product of the projected data. However, the variance is interesting. It's, so we have this A, which is the inner product, and M1, M2, which is the L2 norm of the individual vectors. So therefore, the variance of the inner product estimate is dominated by the marginal L2 norms. So even when A, the inner product is 0, which is actually very common, because in real world data, most of the pairs are close to be orthogonal. So A is very small for most of the pairs. Of course, for the pair you're interested, maybe A is large, but for most of the pairs, it's actually fairly small. So therefore, the variance is actually completely dominated by the marginals. So this is the fundamental reason why random projection is actually is quite bad for estimating inner products. So since random projection is bad for inner product, what's the alternative? So alternative is which we call minwise hashing, which is only for binary sparse data. It's very simple algorithm, very, very simple. And it's so simple that in the end, you say, why do you need to write a paper for that? Yeah. So it's just simple to that extent. And it's much more accurate than random projections for estimating inner product. It's much smaller space requirements. And it's capable of estimating not just pairwise, but also three-ways and higher order interactions. Random projection cannot do more than pairwise. And it's useful for larger scale linear learning and, of course, kernel learning. I don't even want to talk about kernel learning because in larger scale data, you cannot really do kernels. So the difference, if you compare the running time, the difference between kernel learning and linear learning is hour versus month or something like that. So you don't want to talk about kernel learning. And it's also useful for sublinear time near neighbor search. You can build hash tables. And but it's only for binary data. So you may be wondering, why only care about binary data? Interestingly, binary data actually very common in the real world. For many applications like text, binary representation is actually very natural. And in many data sets, if you quantize or threshold the data to be binary, the performance is not going to be affected as much. And in some cases, even the original data not very sparse, after you conducting pairwise or high order interaction, it becomes very, very sparse. So this is a classic example of how to get a binary data. It's called shingling. So suppose when the data binary, we can talk about that binary data as a set or as a 0, 1 vector. So we usually more convenient to talk about set. Set means the location of the non-zeros. So for the binary, so we're using set. So this is a nice way to get a binary, high-dimensional binary data. So suppose a text is called "Today's nice day." If you're using the first order gram, the 1 gram or 1 shingle, you get a set of 5 elements. If you use 3 shingles, you get a set of 3 elements. And industry applications, they use actually 5 shingles or 7 shingles. What they do is actually combine all the shingles, 1, 2, 5. So this way you get a extremely high-dimensional data. So for example, if you only consider 10 to the 5 common English words, after you raise to the 5 power, it becomes 2 to the 83 dimensions. So, but in practice, we do 2 to 64 dimensions because you need a lot of documents to exhaust the dictionary. Otherwise, you get empty columns. So 2 to 64 is convenient surrogates. And so this is our notation. So basically, I have 2 sets. I use F1, F2 for the size of the individual sets, and A is the size of intersections. And for when you talk about binary data or sets, it's more convenient to talk about resemblance, which is a popular measure of similarities, is the size of intersection over size of union, or in terms of notation AF notation, this is the definition is between 0 and 1. It's a very nice measure of, and also intuitive measure of a similarity. So the standard practice is called minwise hashing. So that's how it works. So suppose we're able to do permutations on the total space from 0 to 1, capital D minus 1. And then you do the permutation on the 2 sets, and you store the minimums. And the probability that the 2 minimums are equal is R. Let me give you an example. So here's just a toy example. So suppose the set has 5 elements. So S1 has 3 elements, S2 has 3 elements. So the resemblance is 1, 5. And so this is one realization of the permutations. So 0 becomes 3, 1 becomes 2, etc. So now let's apply this permutation to S1. So let's see, you guys can help me. So 0 becomes 3, so it's 3. And 3 becomes 4, so 4. So the smallest element is 1. So you apply the same permutation to another set, the smallest element is 0. So in this case, the two minimums are not equal. Well, they only have 1/5 chance to be equal. So if you redo this k times, k, for example, 500 or 200 or 1,000, so you become a binomial probability estimation problem. You can actually write down as this is estimator from k permutations, and we can compute the variance. So that's a short tutorial about minwise hashing. And okay, so what are the problems of minwise hashing? So the first problem is that people realized a long time ago is that when you use minwise hashing for similarity search, it requires high storage and computational cost. It's high storage because usually people use 64 bits to store each hash value, and 64 bits is just too much. And so the total number of space is large, and of course that translates into computational problems and the network problems, etc. And more recently, we realized you can actually use minwise hashing for learning. For example, fitting logistic regression. The problem is if you're using that, its dimension is very high. If you do 64 bits, the dimension is 2 to 64 dimensions. So you have to, so that's the problem. But B-based minwise hashing provides solution to both of them. So that's the intuition of B-based minwise hashing. So suppose the two sets are identical, then any part of them are identical. So that means b equal to 1 suffices. Actually, b equal to half also suffices. And so, of course, when two sets are similar, but they're not identical, then we can conjecture that maybe the lowest b bits should be also similar. We need a proof, but we do have a proof. So therefore, hopefully, maybe we do not need too many bits, especially considering applications. For example, duplicate detections only care about similarities, which is larger than 0.5. So for those applications, maybe you don't need too many bits. So that's the proof. So now let's introduce in some probability. So basically, now this is a S1, 2 sets, S2, and we do the permutation and store the two minimum values, Z1, Z2, and we define the B-bit version. So using this so this is a superscript B. So for example, when Z1 is 7, which is a 1, 1, 1 in binary, so then the first bit is 1, the lowest two bits is 3. So that's what I mean. So the probability is actually very simple. It can be written as so the original probability is R, the collision probability, but now the new probability, the probability is actually higher. It is higher because once you add, the probability is actually higher, so it can be written as a C1 plus 1 minus C2 times R. So what is a C1, C2? So they're actually very interesting formulas, and it's fun to get them. Once you obtain this formula, I find this is one of the few times I actually obtain formulas of such a nice form. And I try some other problem, you don't get such an elegant formula. But this is one nice formula. So basically, the formula has to do with the size, relative size of the set. And then define the two constants. Then you can compute C1, C2. And so that's, we have the reference, shows how do we derive them. And we also did the simulation, not simulations. For small d, so this is a closed form. But if you want an exact solution, there's no closed form. Except for small d, you can actually compute it exactly without closed form. So we can see that even though our proof requires d is very large, which is true anyway, but even for small d, the error is actually less than 0.01. So it's very accurate formula. And so we have this plots in the research highlight paper. So from this probability formula, we can estimate the resemblance again, and we can compute the variance. So now we have problems here. There's a variance space trade-off. People talk about variance bias trade-off. Now we have variance space trade-off. If you want a small number of bits, you get a smaller space. However, the variance is larger. So how do we characterize the trade-off? Using space multiplied by the variance. So this B means that. So basically, we use the ratio. So for example, so B64 over B, little b, equal to 20 means to achieve the same accuracy in terms of variance, using 64 bits per hash value will require 20 times more space than using the 1 bit. So that's the definition of this value. We plot this value for all the data, and we can see that when the data dense, B-bit minwise hashing using 1 bit can achieve 64-fold improvements for very high similarities. However, when data sparse, you only achieve 32-fold improvement. If you care about similarity, 50% similarity, you achieve about 21.3-fold improvements. So so basically what this means, if you use 1 bit, you increase the number of permutation by factor 3. You get the same accuracy. So therefore, this is a number 3 comes from. Yeah. And we did some experiments for retrieving pairs of documents whose similarity is exceeding certain threshold, for example, R0. So we have a pool of documents. We want to find all the pairs whose similarities exceeded this threshold, for example, 0.3. So we can see that for low similarities, using 4 bits achieve the same results as using 64 bits. And using 2 bits actually get very close results at using 64 bits. And but for high similarity, we can see that using even 1 bit, you achieve almost same results for high similarities. So if you want the documents very, very similar, point A, you really only need 1 bit. Or maybe you only need a half a bit, or even more aggressively. So what do I mean by half a bit? You can generate 2 bits. You can draw them to get a 1 bit. You still get 1 bit, but what we use a half to mean that. So you get 2 bits and you draw them. And you get 1 bit, but we use a half to denote this, what I mean. So basically, it's a good idea to draw the high similar, for high similar data, you get twice the improvement for high similar pairs. However, if the data not too similar, for example, less than 0.5774, it's better not to try this aggressive idea. But if you only care about extremely similar pairs, you only need half the bit. Yeah, so that's the idea. And so it can also be used for estimating 3-way similarities. So what do we mean by 3-way? So instead of 2 circles, now get 3 circles. We want to estimate the similarity, this little a here. So now we need a probability formula, and it's a fun exercise to do that. Again, we get the probability formula that if you take 3 hash values, the lowest b bits are equal is this simple formula, the z divided by u plus the similarity. So what is z? So z is very complicated, and I'm not going to read 9 by 9, but basically it's a formula, and it's very accurate. And we have derivations and in the newspaper. So basically, but the information for 3-way is that you get a substantial improvement using b-bit minwise hashing. Another interesting message is that if you want 3-way similarity, you need 2 bits, at least 2 bits. So that's something interesting to me. And if you want 3-way similarity, you need at least 2 bits. Yeah. Otherwise, the 1 bit only gives you the pairwise information. So that's for 3 ways. I'm not going to talk too much about it. So now let's talk about learning. So how do we use minwise hashing for learning? Well, for random projection, it's easy. You just project the data, then you use the projected data for learning. For b-bit minwise hashing, is not that obvious at the beginning, because for minwise hashing, the estimator is the indicator function where the 2 hash values are equal. It does not look like an inner product, but if you look closely, it is actually an inner product, because the indicator function can be inner product in very high dimensions. So for example, if we want to test 2 numbers are equal, so 2 numbers range from 0 to d minus 1, the numbers are equal is actually 2 extremely sparse inner product, 2 extremely sparse vectors with exactly 1, 1, and all the rest are 0. So it's very silly inner product, but it is an inner product. So that means in principle, you can use it for learning. So here's an example to convince you this is the inner product. So for example, you consider d to 5. So then we just expand numbers between 0 and 4. So we can expand all the numbers 0 to 4 into a vector of length 5. For example, 0 becomes 0, 0, 0, 1, 1, because we need a 1 somewhere. So 0 becomes 1 at the first location, 1 becomes the 1 at the second location, 4 means the 1 at the highest location. So that's the expansion. So once you do the expansion, so the indicator function, for example, z1 equal to 2, z2 equal to 3, so the indicator function is 0. It's the same as the inner product, which is of course 0. And if z1 equal to 2, z2 also equal to 2, then inner product, the indicator function is 1, which is of course also 1 in terms of the inner product. So it's a trivial ideas at this point, but when you look at the first time, it's probably not that obvious. So now it's clear how to do learning. So now suppose you have a high dimensional data, 2 to the 64 dimension, for example, and you want to do a classification using SVM or logistic regression. And so what we do is 2 steps, very simple. You do the k independent permutations to generate on the binary feature factor only works for binary data, and store the lowest value, b bits, for each hash value. So this way, you get the total storage requirements n times b times k. Then in the runtime, you expand each data vector into 2 to the b times k dimensions. So this is more examples. So now suppose we do 3 permutations and using 2 bits, and we have sets S1, S2, S3. So we apply the same permutation to all the sets. So let's worry about the first set. So the original hash value is, we got 3 hash values. This is three hash values. And if you look at the binary representations, this is binary representations, then you take only 2 bits. So this is 2 bits of the binary representations. However, to do learning, you have to expand them into 2 to the b dimensions, because now the first one is correspond to 1, 0, 3. So that means the first one, the second location is 1, the first location is 1, the fourth location is 1. So therefore, you start with the binary vector, you get another new binary vector. So it's simple as that. Then you apply the same thing to other sets. So it's extremely simple, and works very, very well for binary data. And so sometimes it's just amazing fact that when you look at a lot of things that works, it's all simple. So simplicity look like yeah. So anyway, so this talk I only talk about text data for this data set, for this purpose, this talk. And we're actually doing like image data with terabytes of data, or even higher, and we're still working on that. So the problem with the big data is not really the memory now, it's really the disk. And if you work with single workstations, 2 terabyte disk, it just cannot do much. So that's a problem. And so our data sets are 2 data sets, and 24 gigabytes are 200 gigabytes. The first one is 16 million dimensions, second one is a billion dimensions. And so this is remember in logistic regression, we have one parameter C. So all the experiments will be, results will be presented in terms of C, the regression parameter. So we try C from 0.001 to 100, and we experiment with 30 to 500 permutations, and 1, 2, 4, 8, and 16 bits. So this is the experiment. So now this is web span data sets. We plot the accuracies, classification accuracies on the test data. And this is original accuracy as a function of a regression parameter C. And we can see that with 200 permutations, if you use 1 bit, you're doing something, it's not too good, or it's actually doing reasonably well, 92% performance in terms of accuracy. And if you use 2 bits, you get a much better performance. Using 4 bits, you get almost the same as using original data. And using 8 bits, you get the same results. So in this case, 8 bits and 200 permutations, so that's actually about 70 megabytes only, the data in terms of storage. In terms of dimension, it had to be expanded a little bit higher, but in terms of storage, so that's the cost. So and we can do this for all number of permutations, 50 to 500. We can see the similar kind of trend. This is for SVM. And the testing time, the variance is very small. That means the algorithm is stable. It's a randomized algorithm, but it's very stable. And the training time is changing from about 100 seconds to about 2 or 3, or maybe 7 seconds. And the testing time is reduced much more. So that's good. And so we also see the same thing for logistic regressions. And so for logistic regression and SVM, in terms of performance, they're almost identical, except logistic regression is 10 times slower than SVM. And training time is changing from 1,000 to about 10 seconds or 20 seconds, etc. And if you want to compare with the random projections, we compare with the random projection. We also compare with some other methods called VW, which is in terms of variance, the same as random projections. And we already know that random projections, the variance is dominated by the margin or norms. But minwise hashing, there are much smaller variance. So that's why it's not surprising that minwise hashing here works much better than the other random projection-based methods. In terms of accuracy and in terms of time, just substantially better. And we also have the experiments for the larger data sets, which I'm not going to go over. And so we just did all the work. It's a lot of fun to do this once it works. So we'll have comparisons with the random projections, etc., and in terms of time. But And the final thing, which I need maybe two or three slides, is how to use minwise hashing. Now we know that we can use that for learning, but now how do we use that for near neighbor search? It's easy. So that's the idea. So basically, you do minwise hashing. For example, you have 2 bits and 2 permutations. So that's good index space, okay, of size 16. So now you can do minwise using. So then you only search for the near neighbors on the buckets, and so this is the result. So using, for example, a precision recall curve compared to sparse random sign random projections for near neighbor search. So it's much better than other methods for near neighbor search. You only do how many bits? You only do you only retrieve like 1% or 2% of the data, and you get a very good results. So I guess I'm over time, so I will stop here, and maybe with pointing out the major drawbacks of minwise hashing is that it's only for binary data. It has expensive pre-processing cost, and we can use GPUs, of course, for that, but it's not energy efficient. So that's the major drawbacks.